Today I'm just going to do a review of the types of intermolecular forces that we've talked about in class that we did in our activity. And these are all variations on types of dipole attractions. So first I just want to do a very brief review of the kinds of bonds that we talked about. First up here we have nonpolar bonds. So here the electrons are shared completely evenly and there's no charge on either end of the molecule. Right? And then we also talked about covalent bonds where the electrons are shared unevenly, which is right here. These are polar covalent bonds, and you get a negative charge on one side and a positive charge on the other side. And then just for completeness, we also talked about ionic compounds where we get an electron that's completely transferred from one atom to another, and so we have a full positive charge and a full negative charge in these cases. So first, just the ion dipole. So ions have a full charge, and if you have a polar molecule around that has a partial positive and a partial negative, they'll orient themselves so that all the positive partial charges point to the negative ion, or all the negative partial charges point to the positive ion. And these are called ion dipole forces. All right, the next one we talked about was dipole-dipole. So in this case, we're looking at the partial charges on each of the molecules as a result of the uneven sharing of electrons. And so they'll line up in space so that the negative and the positive are coming together to be attracted. So this could be horizontally in space like this, or vertically in space like this, or we could combine them. So we could also have next to this one a partial minus here and a partial positive here, and a partial minus here and a partial positive here. In two different molecules, right? So we'd have attraction here, and here, and here. All right, and these are all examples of dipole-dipole, and you'll find that molecules will line up to maximize those attractive forces and minimize the repulsive forces. Right? A special kind of dipole-dipole is called a hydrogen bond, and these are just special because the pull from the electrons away from the hydrogen is so strong when it's bound to either oxygen or nitrogen or fluorine that we get an even bigger uneven distribution of charge, so that partial charge would be even stronger than if it was just a regular dipole-dipole. All right, so anytime you have hydrogen that's bound to either oxygen, nitrogen, or fluorine, you get hydrogen bonding. Now, we can also have a dipole interact with a nonpolar molecule and have an attraction because of an induced dipole. And the way this works is the atom or molecule, which we have here, which is nonpolar, gets close to a molecule that has two different charges on the two different sides, a molecule that's polar. And for example, if we have a negative here, the electrons that are in our nonpolar molecule or atom aren't going to want to be near there, so they're all going to move over this direction, and we're going to get some positive charge over here because the nucleus will be more exposed, and the electrons will all be over this direction because they're trying to get away from this negative charge. So when this happens, that's called an induced dipole. And because now we've induced a charge on either side, it can interact in an attractive manner with the dipole that's already there in this polar molecule. All right, and then the last one is that we can have two induced dipoles interact with each other. So if we have two atoms of helium, for example, helium has two electrons, and they can move freely about the atom. And normally, there's no difference in charge on one side or the other. But as we talked about with the sheep in class, if you have two that are floating around, so maybe you have them like this sometimes, and then other times they might just by chance both end up over on one side. And when that happens, we get this, which is an induced or an instantaneous dipole. And then when that partial positive charge over here interacts with this atom over here, it causes the electrons to want to be over on this side more. And then we get another dipole in the other helium atom. And so these are much, much weaker than dipole-dipole interactions or than hydrogen bonds, but they do happen, and they are significant. And they're going to be the strongest when you have more electrons to move around. So as the mass of your molecule or atom goes up, the strength of the induced dipole interactions are going to also go up. And one other thing to note, I frequently call these interactions London dispersion forces or just dispersion forces, which is what my other textbook uses, but you should know that they can be used interchangeably and they mean the same thing. All right, so that wraps up our discussion of attractive forces between molecules. These are intermolecular forces, and we're going to explore how these affect the way molecules are going to interact with each other and their reactivity and their ability to dissolve in things and all that kind of stuff coming up next.